Hello, this is lab assignment number 2 demonstration video for EE542. So in this lab, we are setting up an example topology in an AWS virtual private cloud. So here we have a client device, a server device, and a router. The three virtual machines are connected in point-to-point connection. Server and router has a connection in this specific subnet, um, and the router and the client has a connection in this specific subnet. And the server and client also have two interfaces which is used to connect to the external internet, and we can connect to these specific instances using SSH and uh, assigning a public IP address to the specific virtual machines. So this is the network which will be tested on AWS, and I will go through the AWS setup now. So for setting up AWS, the first thing which has to be done is creating a virtual private cloud where all your instances of the virtual machines are set. So initially we have to create our own VPC. So to create a virtual private cloud, we just click on create VPC and assign a IPv4 block of addresses. So the block which I have used is 10.0.0.16. So you can use any other network. So this is a /16 network. So 16 bits can be used for assigning to the host devices in this specific network. And then we just have to click on create VPC here. I have already done that for this specific lab. So this is the VPC which I've created. And if you see the address which is assigned, it's 10.0.0.0/16. So that's the step which is used to create VPC. And for the next step, in order to set up this connection, these connections which are shown in this topology network, we need to set up subnets which are associated with that specific VPC. So we have four subnets. So one of the subnet is used to connect between the server and a remote host for SSH, and another one for the client. And then we have connections between the client and router and server and the router. So all of them belong to the same block of addresses which is provided to the VPC, but we have different specific subnets here. So these subnets which are shown here are according to what is configured in this topology. So if we see here, the server and the router is connected to using 10.0.2.0/24, and that's what is seen here. And the server is we can connect to the server using SSH in this specific network 10.0.1.0/24. So to create a subnet, we just need to click on create a subnet and select the specific VPC which we have created, and then we need to provide the subnet name and then the IP address allocation for that specific subnet. I've already done that, so I won't be doing it again. So once the subnets are created, we need to set up an internet gateway. So these internet gateways are used to connect the virtual private cloud based instances to the internet. So for that, we have the internet gateway which has to be configured. So to create an internet gateway, we just need to click on this create internet gateway and provide a name. Once this is done, we can attach a virtual private cloud to that specific internet gateway. But since both of my virtual private clouds already have a internet gateway attached to it, I'm not able to see it here. So this is how we can create an internet gateway. Once the internet gateway is set up, we need to set up routing to the internet gateway. Basically, all devices which are uh, on the internet should be able to connect to the internet gateway, and through the internet gateway, we should be able to connect to the different devices on the virtual private cloud. So in order to do that, we need to use the route tables. So here we need to find out the specific. So as soon as you create a virtual private cloud, a route table is created which is associated to that specific virtual private cloud. So we just need to add a route which allows for all devices to connect to that specific internet gateway, which is already done here in the above step, so I won't be doing it. So once that is done, we just need to save the changes and it will be added to the routes. So with this setup, we are able to connect from an external source to the virtual private cloud, but we still don't have a public IP address associated with the devices which is present in the virtual private cloud. So we still will not be able to connect unless we configure elastic IP addresses. So what the elastic IP address does is it associates a public IP address to a specific virtual machine in the VPC. So we need three of those because we need to connect to three different uh, hosts on the virtual private cloud, including the client, server, and the router. So that's strange. Yeah. So I have already created three different elastic IP addresses. So once the allocate the elastic IP address, we need to associate with the network interface, which is corresponding to that specific device which we are trying to connect to. So before we do that, I will configure the EC2 instances for the machines which we are trying to simulate. So we need three different instances for each of the devices which we are trying to simulate. So client, the VIOS router, and the server. So I'll just walk through a specific instance creation step. So here I'll just create a example instance. So for the server and the client, we are using Ubuntu OS. So we just select Ubuntu, and whichever is the free tier eligible one, we can use that. And yeah, so once that is selected, we need to select a key pair which is used to connect uh, which is used in the SSH connection. So I've already created a key pair. So what we can do is we can click on the specific key pair which we are trying to use. Okay, once that is done, we need to configure the network settings. So here Uh, yeah. So first we need to select the VPC which we are trying to connect to, and then the subnet which we are trying to configure the specific instance in. So for the server, the we configure the instance in this specific network, and for the client in the specific network, and for the router it can be either of these. And once we select the network, then the network settings are done. We just need to add new security groups. So what the security groups does is it is similar to a firewall where it prevents or accepts only specific connections to the devices on the network. So the SSH rule is all added by default, where all connections from outside are able to reach the specific instance on port number 22. uh, it should be able to also use all types of TCP connections, because we will be testing TCP connections, and all the specific addresses should be able to connect use TCP to this for the specific instance, and then do the same for UDP as well, and then also we need to do the same for ICMP. The ICMP protocol is used for ping, and yeah, mostly for ping, and we do the same where all the specific IP addresses are able to connect to the specific VPC. So once that is done, we also need to configure a second network interface, because each specific device has two specific interfaces. The router has these two, and server has these two, and client has these two. So based on that, we need to select the right network interface subnet, because we need to configure the network properly. And once that is done, we just need to click on launch instance, which will create the instance for us. So I've already done the setup for client VYOS and the router and the server. So it's already set up and running. Yeah, so once that is done, now we need to figure out the connection between uh, the we need to figure out SSH connection between the host and the virtual private cloud based instances. So for the client, we have already decided that the network 10.0.1.0 is what we use for SSH. So what I can do is I can go to the client instance and then go to networking, and I need to figure out which interface is linked to that specific uh, that specific subnet. So for the client, it's 10.0.3.0. So that is the specific private IP address, and this is the interface ID for that specific interface which is associated with this IP address. So it starts with 04DC. So now I need to assign, since we are trying to SSH to that specific interface, we need to assign and create an elastic IP. So creation is just this much. And once that is done, we need to associate this elastic IP to the specific network interface. So that is why we need the specific ID. The 04DC ID would be able to connect to the specific client device. Yeah, so I've already done that for the three different devices, for the client, the server, and the router. So yeah, the setup is already done. And once that is done, it can also be seen in the instances tab here if we see elastic IP is assigned to each of the devices. Okay, now that the setup is done, we can go through the SSH connection. So as we created the key value pair, we need the specific private key file in our local system. So once we have that, we can connect to the client and the server. So you need to figure out which IP address, which public IP address is assigned to which specific device. So it's seen here for the client, we have the 100.21.120.106. So I also need to provide the uh, private key file. So the connection is set up for the client device. I do the same for the server. And also for the router. So for the router, the username is based on the OS which is being used. So for the router, it's VYOS, and the public IP address related to it is this. Yeah, so the connection is set up. So if we see the VYOS has already set up the routes where the specific packets have to be sent to. So for this specific network, it's Ethernet 1 interface. So yeah, so this is ETH1 and this is ETH0 in case of VYOS. Yeah, and for the servers, me just do ifconfig just to confirm that this is the server device. We see the server should belong to 10.0.2.0 network and 10.0.1.0 network. So if we see here, that's what is seen. So Ethernet 0 is the one which is connected to SSH, and 10.0.2.0 is Ethernet 1 which is connected to the VYOS router. And for the client device, it's 10.0.3.0 and 4.0. So if I do ifconfig, 3.0 and 4.0 network is seen here. So now we have the connection setup completed. So let's do the network performance analysis. Before that, we need to go through the questions which are present here. So um, yeah, so initially we need to set up the routes for connecting the uh, packets which are sent from the server to the client and from the client to the server. So let's execute that. So on the server, I need to route all packets to this 10.0.4.0 network to this specific interface, which is ETH1. So this is the command which is executed. So here, what we are doing is we are adding a route to the specific network, which is the server and the router and the client network, and then we are passing that to this specific IP address, which is the IP address of the router uh, on the server router network. So that can be seen if you do if config here. Uh, uh, or if config does not work on vivoOS, so we can see here the th1 uh, interface has the same IP address which was shown here. So I've already added it, so that's why it says file exists. And the same should be done on the client as well. So add a route which says that all packets to the specific network, which is the router and the server network, to go to the interface which is connected to the client. And I've already done that on the client as well. Now, just to confirm, so this is the IP address of the client on the this is the IP address of the server on the server and the router network. So if I ping the ping seems to be working. Now just to confirm that we are going through the right route. Yeah, so this is the IP address of the router, and then this is the IP address of the client. So the route is set up and we are able to ping as well, so the communication seems to be working fine. So we have set up the route already. So SSH will go down if the IP address on this interface is changed, because we have allocated the uh, public IP address to a specific interface. Now, if the IP address is the elastic IP is changed, that means SSH connection will not be able to continue because SSH is using that specific IP address. So DH client is basically set asking the server to asking asking a DHCP server to set up a DHCP address, set up an IP address for the interface. So we can start the DH client on a vivoOS VM using this specific command. But since the IP addresses are already assigned, I don't need to uh, set up any extra routes, or I don't need to add any extra uh, connections. Uh, so the specific file doesn't exist anymore on the AWS instance. So we don't have any cloud override scripts as of now, or it's possibly moved to another file. So this installation is also already done. Uh, so VMs are not able to, so in our case the VM is able to contact the internet, and this possibly did not exist like by default previously, and that should be because of DNS maybe. But in our case, the VMs are able to contact the internet. So if I do, because the Google DNS server seems to be responding to the server uh, device. So we have internet connection. So the sudo apt-get apt update command, it checks the sources and updates all the package information, and we can use it to install any new packages which we need. So I've already installed iperf and iperf3 on the client and the server VM, so that's already set up. Now I will start with the iperf measurement. So the first command is to test the UDP and TCP throughput through the connection on the server and the client. So I am starting before we do that, I also need to check the TCP dump example. So I'm listening in to the specific interface on server. So if I do execute the ping command, we can see the ICMP echo request and echo reply, which is used for the ping command. So basically, this specific let me just stop this. The specific IP address, which is the client IP address, is requesting this specific IP address from the server, and that's the request. And we also see the reply from the server to the client. Now the ping request which I'm sending to is this specific IP address, which is not the same here, but this is the other interface on the server. So basically I'm pinging and that the request and reply seen here. And if I use trace route, which uses UDP, you see UDP packets here. Okay, so that TCP dump is done. Now I will set up the server on the iperf using iperf. And I will send data from the client. So this command basically tells that this is the client device and we are connecting to the server on 10.0.2.184, which is the IP address of the server, and I'm setting the bandwidth to be 10 gigabits and I'm using UDP. Before this, so I had initially set the MTU to be a smaller size for previous experiment, so I removed that specific change. So I will do the setup again. So this is the server and this is the client. So I'm trying to set a very high value so that we overwhelm the server and the receiver so that we can check the bit rates. So we see that with the UDP, we get a bit rate of 1.40 gigabits, which is probably the limit for uh, the NIC or the network. And we see that there's a huge amount of loss, which is 27% for UDP. Now I will use TCP. If we can see that the bitrate is reduced, but and we have some retransmissions, which means that some of the packets are lost, but the bitrate is constant on both sides. But it's less than UDP because UDP does not check the bandwidth or check the losses with respect to uh, with respect to its transmission. So it just keeps transmitting stuff. There's no reliability or there's no checks for uh, the round trip time or whether the packets are lost. So that's why we have a higher bitrate, higher transmission bitrate with UDP, but the a lesser one in case of TCP. Now we need to add delay in the network, so it can be done using this command. Also need to add it in the server. So what we are doing is we are using the queuing discipline which is used in the specific device. We are adding for specific Ethernet 1 interface, we are adding a delay of 100 ms. This and netm is the network emulation tool, and then we are adding a delay of 100 ms. So what this does is this increases the delay on the server and the client for transmissions to 100 ms. So just to confirm, if I ping from the client to the server, we have a delay of 200 ms because there's a delay which is added on the client and the server which is equivalent to 100 ms. And if you see the previous ping command, it was like almost 1 millisecond, but here the the round trip time is 0.936, but in this case we should be getting 200 ms almost. So the we have added a delay. Now let's set up the server. And with TCP connection, we can directly see that the bitrate is reduced drastically compared to the previous example. And this is because the round trip time of the connection has significantly increased. So TCP sets its sending window or the amount of bytes which can be sent based on the round trip time of the packets. Now, since round trip time has drastically increased, the window size has decreased. You can see that there are no packets which are lost here, but the amount of data which is sent is drastically reduced compared to the previous step. Now, if we use UDP, we can see that the bitrate has increased. The transmission bitrate of the uh, device on the specific network has increased. Now, this could be because of a couple of reasons. The major one would be that since we increase the round trip time, the network interface card is not overwhelmed with packets. So because of that, we are able to like transmit all the required data from the NIC because it takes a long time for the data to be received back from the server. So we reach almost the bitrate which we are trying to simulate. But in case of but the amount of loss is very high compared to the previous case where we had around 30% loss, but in this case we have 92% loss. This just means that with UDP we are able to send a larger amount of data, but there is no reliability in this case. Now we have set the delay to 100 ms. Now we set the delay to 0% and the loss to 10%. So for this queuing discipline, for this interface, we are setting the delay to 0 and the loss to 10%. So now we do the same with UDP, I mean TCP, and we can see that there are a number of retransmissions because of which the bitrate is drastically reduced, because based on each loss, the TCP treats it as a uh, uh, issue with the network, and because of the congestion control algorithm, the window size again reduces drastically. So because of that, we see that the bitrate is reduced. Now if we go back to UDP, we see that the bitrate has gone back to how it was previous to setting the delay to 100 ms, and this can be seen here. It's around 1.53 to 1.40, which is almost what is seen here. So there's no effect on UDP because UDP does not care whether the packets are lost or not, but we see that there is a huge amount of loss in the iperf uh, log. Now we have done the experimentation with the loss, and now we can check the kernel logs using the specific command on the server or the client. So just we just connect to the server 44 to 26 is the IP, and I just need to execute this command. So I see that there are no kernel logs on the server, so let me just open the uh, client device and see. It's 100.21. Yeah, so as we see, there are some kernel commands, but this iperf logging is a user space program. So during the execution of iperf, we may not see any packets or packet information or like transmission information here. So let me just execute command and see if there's any updates. No, there is no updates here. Basically, I don't see any commands, any logs related to the transmission of data, but there may be some data which was there previously in the kernel. But during the execution of iperf, I don't see any updates here. So I'll just delete all the configuration which I have done till now. Uh, and then I will execute the command for setting the rate of the interface. So in this case, what we are doing is we are using the token bucket filter rate. We are setting the rate to like 100 megabits, and then the latency to be 1 millisecond, and then the burst to be 9015. So what this does is it allows the maximum size of the uh, Ethernet frames to be sent on the bus. So if we set burst to be a high value, that means like we are able to uh, transmit more amount of data on the bus. Now instead of 10 uh, gigabits, I'll just use 200 megabits bandwidth. Now we see that for uh, TCP there is no change. Let me just uh, use UDP and see. Uh, so so I have not executed the command on the client side as well. So for the setting the rate to be 100 megabits and the latency to be 1 ms. So I'll just execute it again. Uh, yeah, so once that is done, I will just execute the commands again. So for TCP connection, we see that even though we set the bandwidth to be 200 megabits, we see that the bitrate does not exceed 100 megabits because we have set the token bucket filter rate to be 100 megabits, which means the queuing model in the NIC on both the devices will be set to 100 Mbps. But we see that there is the bitrate is still less than 100 megabits because TCP, based on the number of retransmissions which has happened, it will see that there's congestion in the network and it will limit the window size. Now, if I use UDP, you see that the bitrate is not limited because UDP does not care about the bandwidth that keeps sending how much ever data is available to be sent on the network. And we see that all the 200 megabits of data bitrate is set to 200 Mbps, but we see that there's a loss of almost 50%, which means the since we set the token bucket filter to be 100 megabits, we see that there's a loss of 52%, which means the bitrate still comes down to below 100 Mbps. But it's still higher than the bitrate which is seen with TCP, which assumes that there's a loss in the network and takes steps in order to reduce the window size. So we can try executing the specific command. So we see that this operation is not supported. This is because we are not able to set the speeds of the NICs which are used in the EC2 instances because these are set by the AWS cloud itself, and we need to like try out different tiers in order to tiers in order to change the network speed, and we are not able to like control the network speed by ourselves. So since this is not a private device which is used by us, we are not able to change the speed of the device. So let me just delete all the configuration again. And as mentioned, I will add the same configurations on the VYOS or the router device so that we observe the behavior. So let me just add the delay. So in case of VYOS, both the network interface cards which exist in the device are used for routing. So I'll just add to both the devices. So for ETH0 and ETH1, and then try to set up the server and the connection. You see that the bitrate is very less for TCP. This is because TCP again assumes that because of the large round trip time, the whole network is congested, and it basically controls its own transmission by reducing the window size at the transmission. We see that there are no retransmissions, but since the delay is increased, we see that the bitrate is drastically reduced. For UDP, we see that there is no change with respect to the initial configuration which we had. This is not the same as adding a loss at the transmitter or the receiver, because of which the network interface card will not be overwhelmed. So we are adding a delay in the uh, intermediate node, which is the VYOS router, because of which we see that there's no change in bitrate. But in case if we add the delay in the router or I mean in the server and the client, we see that the bitrate increases drastically. But in this case, we see that there's no change in the bitrate, which means that bit uh, adding the delay in the VYOS router has no effect on the UDP communication, but we still see that there's a huge loss, higher than what we have generally for the normal communication. Now I will set the delay to 0 and add 10% loss. So now if we carry out the communication, we see that there's no change in the bitrate for UDP, but we should see that there should be a large amount of loss, 37% loss. Now this is not exactly the same as 10% loss which we have like set for the device. This can be uh, checked by setting the bandwidth to a very low value. So for 100 megabits. Oh, so this is TCP communication. Let me just uh, use UDP communication first. You see that we transmit 100 megabits worth of data, but there's 10% loss in the data. So because some of the packets at the VYOS device are dropped. Now if we use TCP, we see that the bitrate reaches nowhere as close to what is expected. And that's because each time there's a loss, the window size is adjusted by TCP based on the congestion control algorithm, where the window size is halved at the sender, and because of which the bitrate never increases above a specific value, and it's much less than what we see for UDP. And we've tried with delay and we tried with the loss function. Now let's set up the uh, setting the uh, token bucket filter rate and the setting latency to 1 ms and setting a high burst rate for both the interfaces on the VPOS router. And now, since we have set the token bucket filter rate to be 100 megabits, I will set this rate to 200 and check the TCP communication. So in TCP, we see that based on the retransmissions, we are adjusting the congestion window and the bitrate is reduced. And these retransmissions exist because the bandwidth is limited at the BYOS router, so we limit the amount of packets which are sent. Now, in TCP, because at each retransmission, the window size is reduced. If we use UDP, we see that 200 megabits of data is sent, but we should be seeing a huge amount of loss because the rate is limited uh, at the router. So with this, all the testing is done for the uh, network performance measurements, and do the same step, not map to an elastic. So I will just go ahead with this step. So in this step, it's mentioned that we are only required to do the configuration on the interface which is not mapped to elastic IP, because then it would also affect our SSH connection, since if we have 10% loss on the uh, connection to the SSH device, then there's an issue with TCP and UDP connection. So SSH basically, which uses TCP, but I have like configured it on both the interfaces to see the behavior. Now, if I delete all the configurations, that should be it for the network performance measurement. So this lab is completed. Thank you.